I want to introduce another topic today. This one involves debugging a Verilog design that's running on an FPGA. And I'm going to start with the same blinky light project that we developed in the last lab. There's been no change to it. And what I want to be able to do is inspect the signals that are on the internal signals that are in the design and be able to verify that they're functioning correctly. Now theoretically I could use an oscilloscope or an external logic analyzer, and I could wire up the scope to the board, and I would be able to see the voltages that are present on the I/O pins. And if I'm not seeing any I/O, all I know is that I'm not seeing any I/O. I know that there's some kind of a problem internal to either the logic of the Verilog module that I've designed, or in the assignment of the Verilog module to the pins, or that there's been an electrical fault. So for example, maybe there's a dead short on a line and I'm actually risking damage to the part. Or there's a break in the line and I'm just not going to get the signal. So there's a number of things that we can do, but knowing where to start looking to resolve those is more than half of the battle in many cases. So to get started, what I want to do is I want to look at the internal state, and to do that I'm going to use a piece of intellectual property that comes with the Vivado tools. It's called the ILA, the Integrated Logic Analyzer, and I'm going to add this to my design. And so I'm going to start over here and use the IP catalog, and this brings up a browser window that I can browse through, and I'm going to look for debug and find debug here, and I'm going to look for the ILA. We can have up to 64 probes defined in our ILA core. Each probe would correspond to some set of resources that I want to be able to trigger on. For this simple example, we're just going to go ahead and use the one probe. The monitor type is allowing me to either inspect native Verilog code or to inspect the communications that are happening between two different devices in the AXI bus. This is the communication between the ARM processor core and Verilog modules, but we'll look at that separately. We'll do a whole other series of videos on that integration. The sample depth is allowing me to configure how much memory I want to be able to dedicate toward collecting the samples. For every bit that I store, I'm going to be able to store up to, in this case, 1,024 samples of that bit. So once I start to trigger, the trigger is going to start recording the data, and I'll have up to 1,024 entries. We can easily change that and go, up to quite a large amount of memory here, 131,000 samples. We don't need anything close to that. The memory is coming from onboard memory in the fabric of the FPGA, what they call block RAMs. There are static RAMs that are available. They're scattered throughout the fabric of the FPGA, or is going to use the flip-flops that are built into the logic cells of the FPGA. We don't really have a whole lot of configuration control over that, but certainly the more memory that I'm using for the ILA, the less memory I would have for a design. And so for these very simple designs, it's hard to imagine that there would ever be memory pressure. But as your designs start to get larger and you start to use those block RAMs for things, this does become a limitation. We can use comparators. This is going to define how we compare values on the probes. This will make more sense here in just a moment. And then I can have a trigger out or a trigger in port. So this would allow me to, for instance, have a trigger out that I could connect to a pin on the FPGA, and then I could connect that to this port on my oscilloscope, and I could actually have hardware software co-debugging, where when I trigger on the logic in here, it starts this oscilloscope to trigger, and the oscilloscope will then watch the data lines on the electrical side, and then I could very easily compare the two and look for differences. Similarly, I could have an external trigger in port where if the oscilloscope has determined, say, a runt frame that would trigger the ILA to start capturing the data and allow me to actually look at what was happening right before that runt frame was generated on the oscilloscope. And so when you have these differences, it can be very desirable to be able to lock these two together. We can have a capture control that allows me to essentially decide what data goes into the memory. So for instance, once we start triggering, we could maybe not actually store all data. We could define conditions that the data have to be meet in order to be recorded in a memory. And then we can decide if we want an advanced trigger. The base trigger allows me to do things like is a signal high or is a signal low. Advanced trigger allows me to do things like edges, pulse widths, and things of that nature. We'll just turn that on just to see what's going on here. So now I'll go into the debug probe ports, and I can now configure the different values that are associated with these ports. As we see here, this probe, I can specify the number of bits, and we could actually just use the one probe and then connect each bit of the probe to one of our signals. Or I could make multiple probes. So if we think back to the blinking light example, for instance, we had the LED out, all 8 of those. We had the clock divider, and then we had the input clock. Let's just go ahead and capture what the 8 LEDs and that divider clock look like. So I'm going to have 2 different probes. One probe will be 8 bits wide, and that would be the LEDs. And then the other probe, of course, will be the div clock. So at this point, it has created a IP instance, and it's now going to generate Verilog stubs that I can use to instantiate a module. All right. If I look at this ILA XCI, this is the kind of template file that's used to generate the rest of the files. If I zoom into it a little, what I see is a Verilog file. And this is useful because if I open this Verilog file, we see all of the kind of parameter probe kind of preamble. But really what I'm interested in is right here. This is the module declaration. And so if I copy that, I can go back to my blinky light example. I'll just paste in this module declaration, and I'll turn this into a unit instantiation. Now, the clock that we want to run on is going to be div clock, and the probe here is going to be the LED out, and so that would be LEDs and div clock. So it turns out the Xilinx tools have a limitation on the Xilinx or the ILA clock, and it has to be at least as fast as the JTAG cable. In this case, I'm going to go ahead and take out the clock divider. I was unaware of that limitation. If you generate the module, you won't get any errors, but at the very end, when you program the device, you also don't get a debugger. So we'll go ahead and just use the high-speed clock, the 100 megahertz clock. And what I've done is I've turned on, let's go back here to the project manager. I've turned on advanced triggering, and this will allow us to turn on and look for more advanced patterns in our debugging. And I've also included now the direction port. So I'll go ahead and regenerate, and once this is all done, we should have a hardware debugging window. Okay, so after some wailing and gnashing of teeth, We finally have our hardware programmed and configured, and an ILA core is available, and it's kind of a great deal. So this is the ILA window, and what we see here is the trigger configuration, and so we can choose the trigger mode. We can see the capture mode, and we can see the refresh rate, which is going to configure how fast this refreshes. We see the status of the debugging core and the capture status, and here we see the rules for setting up the triggers and the captures. So we could do a very simple trigger and say that I want to trigger on LEDs, and instead of having it be bit 1, I want to have it be on bit 4. And now if I click on run, we'll see that it takes just a few extra seconds. And there it was waiting for trigger, and then once that trigger condition happened, and then it shows you the remaining 32,000 samples. So the basic trigger allows me to define a trigger condition of one particular value, whether it's equal to or not equal to, or less than or greater than. The more advanced trigger options are available here under trigger mode. So to create an advanced template or an advanced trigger, we actually had to use the Xilinx advanced trigger, and Xilinx have created an entirely new language to define the trigger mechanism for an advanced trigger. Just what we needed, yet one more different programming language. When I switch over to this trigger setup window turns into a text editor. I'll click on this maximize button to be able to bring it to full screen, and I can use these little idea light bulbs here to get an idea of what the syntax for this language looks like. And this is a trigger on the 4th rising edge. I want to trigger on the falling edge of LED 6. Since LED 7 is not turning on, I want to find out what's going on when that happens. So I'll just copy and paste this as a starting point. And what we can see here is a kind of a basic grammar where we have a state defined, and we give it a name and a colon, and everything that belongs in this state is kind of underneath of it. We have an if syntax, which is pretty familiar for us. We have the same kind of Verilog ease for defining different conditions. Only we have some weird symbols here for R, and if we were to guess for rising edge, F for falling edge. So if I wanted to capture the falling edge of my LEDs, and that was listed as signal OBUF, is an 8-bit wide field, and I don't care about any of the other values. We could define the trigger like this. I'm getting rid of the counter since I really just want to get the falling edge. So we'll trigger, and if it's not that, then we go back to the trigger state. So this little language here allows us to essentially say, if you find the falling edge on bit 6, trigger, otherwise go back and rearm the trigger and look for the next signal. It's kind of the short end of it. I'm going to save this, and I'm going to run this trigger, and we see right away that it did happen. We got to the falling edge of our trigger here at the very beginning. Oh, I had it set for rising edge, so we'll change that to falling edge, and we'll rearm. Okay, so this time we get to see the falling edge happen. And so when the trigger happens, trigger LED 6 went off and LED 5 came on. Yep, I do see the problem. So when direction is equal to 0, I'm shifting only bits 6 through 1 down, never bits 7. And so that would actually be the problem with that rotation. So this was only a 6-bit wide field, and our concatenation here didn't fit it. So that's one problem with concatenations in Verilog, is you have to make sure that they're the right width. So one last thing I want to show as far as using the ILA core for debugging is to set up that trigger out or the trigger in. Let me go ahead and do a trigger out here, and the idea now is when we regenerate this module, the Verilog header is actually going to have another port that I can use, and that will allow me to specify an external connection on the Z board that I can then hook up to my oscilloscope and have that trigger on the ILA core trigger the oscilloscope to also capture. Okay, so after the core has regenerated, I can go and open up the Verilog stub for our module here, and I actually get to see a new template. If I go my Blinky logic here, I can paste this new version of our ILA debugger into it. So neither of those change, but now I have my trig out is going to be my, I'll call it X trig just to keep the signals a little bit different. And then our trig out ACK would be the acknowledgement that the trigger has happened. Now, if you're using a conventional oscilloscope, you may not be able to generate that acknowledgement signal, and so we're going to have to generate that ourselves. So the first thing we can do here, we'll make a register called trig out ACK, and it will initially be 0. Got a syntax error here. Oh, debugger is already declared. And of course we don't have that X trig signal, so we'll come up here and output wire X trig. And now the only thing I've got to do is I'll add an always block here, so always add the positive edge of X trig begin, trig out ACK equals 0. Now that would always turn the clock on. What we might want to do is have this be at, let's see, maybe the positive edge of the clock. If X trig equals 1, let's begin. So there's a little logic block that would essentially raise the acknowledgement whenever the external trigger goes high and drop it whenever the trigger goes low. We could add something more sophisticated. For example, we could hold it high for some number of clock cycles if the scope was relatively slow, whatever the situation is, but just to kind of give you the idea. But this will clear the acknowledgement signal and make us ready for the next trigger, and not have to have that be handled externally. If I were to generate this, then I could go through the process that we've used before to assign this to an external pin, give it a location on the FPGA, and then hook up my oscilloscope's external trigger wire to it, and be able to trigger the oscilloscope whenever the ILA core triggers or the internal trigger condition matches. So there you go. There's just some brief ways of using the onboard ILA debugger.